Okay, so in the previous, well, we didn't meet, but the previous lecture, recorded lecture, we ended up going through looking at an energy-based method for deriving equations of motion. We're going to end up looking today at Lagrange's equation, which is effectively another type of an energy-based approach for deriving equations of motion, except that in what we saw here, this only works for single degree of freedom systems and they have to be conservative as well, meaning no damping, no forcing applied to the system. For the Lagrange equation, we will be able to apply that to multi-degree of freedom system, and as well as systems with damping and with external forcing as well. Okay, so we're going to start chapter or section 1.5, Lagrange's equation. This is a method for finding equations of motion. It's based on, well, it's part of a class of techniques called analytical mechanics. Newton's second law is all based on vectors, and we call that vectorial mechanics. What we're going to do today is based on scalar quantities, such as energy, and it's called analytical mechanics. We are not going to get to do a full derivation of the Lagrange's equation because that relies on Hamilton's extended principle, which we won't cover in this class. If you're interested, it's discussed in chapter 6 of the Meyerowitz book. Okay, so first we're going to just talk about what a degree of freedom is, and then we're going to talk about generalized coordinates. So typically, a degree of freedom is defined as just the number of independent coordinates or parameters needed to fully describe the position and orientation of a system in space. What I like to think of a degree of freedom is just the way in which a system can move. And then, in that regards, any kind of constraint equation you might have works to reduce the number of degrees of freedom or works to constrain how a structure can move. And so with that being said, you can identify a degree of freedom by looking at a system, picking a body, fixing all other objects, all other bodies, and then asking, can the system move if I don't fix one of those components? And then you repeat this process for each body or each object in the system. And I have a couple examples here, and we're going to start by just each of you take 30 seconds to look at these examples, ask what happens if I hold the first mass, this mass right here, if I hold this mass still, can anything else in the system move? Do that for each of these systems. Take about, let's say, a minute, and I'll time you. After a minute, I want you to discuss with your neighbors. And while you're discussing, I'll come walk around and maybe jump in. All right, go ahead and discuss with your neighbors how many degrees of freedom do you think there are in each of these systems? It seemed like everyone is starting to reach a consensus. So for this first system, if we hold one of the masses fixed, then the other mass can move. And if we hold both masses fixed, nothing else can move. And so in this case, there are 2 degrees of freedom, which will say are x of t and y of t. For the pendulum, there's only 1 degree of freedom. In that case, it's theta. And just to have a comment on this, the degrees of freedom are not dependent on the forces that act on a system. And so the forces can act in whatever direction you want and has nothing to do with the degrees of freedom. Degrees of freedom are purely to do with how a system can move. And that being said as well, you could think of describing the motion of the pendulum using Cartesian coordinates or x and y. And in that case, you end up with 2 coordinates, but you'll find a kinematic relationship between those two, which then gives you what we would call a constraint equation and reduces it down to only 1 degree of freedom. For this third system, we have 3 degrees of freedom here. First, if we let's just fix the bar completely. In that case, the only thing that can move is that mass, and it can only move up and down, so that's 1 degree of freedom, so it's y of t. If we fix the hanging mass, and let's say the rotation of that bar, the bar can still move vertically. And if we fix the vertical motion, but not the rotation, then it's allowed to rotate. So that is how we know there are 3 degrees of freedom here. Read off. And those are x of t, y of t, and theta of t. Okay, so in general, the number of degrees of freedom is going to be equal to the number of equations of motion. Your notes have an error to say each degree of freedom is governed by its own equation of motion, and that just means that the number of DOFs is simply equal to the number of equations of motion. This is always true. Of course, that takes into account kinematic constraints. So the number of coordinates you choose to use to describe the motion of the system may be larger than the number of degrees of freedom, and that's where these constraints come into play, or geometric relationships, we can say. Okay, we're now going to talk about what are considered generalized coordinates, and this builds upon what we just discussed with degrees of freedom, and very much heavily related. Any questions on degrees of freedom before we continue? Okay, so in most dynamics problems, a good choice of coordinates is going to eliminate a lot of difficulty. For example, in the pendulum, if you choose to use theta rather than x and y, that's going to drastically simplify the analysis. And so the goal when you're choosing generalized coordinates is to eliminate the difficulty that arises when you have extra coordinates and those kinematic constraints. We're going to just take a look at a motivating example here. And in this case, we're considering two masses that are moving in the plane and are connected by a rigid link shown here. I've gone ahead and I've drawn three different position vectors, R1, R2, and then RC, which is at the center of mass. So first, we're going to define two position vectors, R1 and R2, for each mass. R1 is going to be equal to x1, that's x1 in the I direction, plus y1 in the j direction. Nothing too complicated there. That should not be an xi, it should just be x1. R2 is equal to x2i plus y2j. And here we have four coordinates that describe the motion of this system. However, there is a kinematic constraint that relates these four coordinates together, and that constraint is that x1 minus x2 quantity squared, and so when I say quantity, I mean everything in that parentheses. So that quantity squared plus the quantity y1 minus y2 quantity squared is equal to L squared, with L being the length between the two masses. And as a result of this kinematic constraint, there are only three independent coordinates, and therefore there are only 3 degrees of freedom. And so we've happened to choose a set of coordinates here that are not the generalized coordinates for this system, and hence why we end up with this kinematic constraint. Okay, so an alternate set of coordinates that we can use instead that does not lead to a kinematic constraint are the translation coordinates of the center of mass. That would be an xy for the center of mass, plus a rotation angle, let's say the theta I've drawn there from that horizontal. So those are the 3 generalized coordinates for this system. Knowing those 3 coordinates at any given point in time, if you know that, then you can determine the position of both masses for all time. And you do not need a kinematic constraint equation. And so I also want to point out that a set of generalized coordinates is not necessarily unique. There can be many generalized coordinates for a particular system, and they can, as long as they're all independent, you can choose whichever one you prefer to use. Okay, so just to give another simple example here, we have a pendulum shown here. Earlier when you looked at it, we used the angle theta as its degree of freedom. However, you can also describe its position using alpha of t, theta or phi of t, y of t, x of t. Any of those will work. Well, x and y you have to use together. Alpha, phi, or theta you can use independently or separately. Okay, so x and y here are not generalized coordinates because they have a dependence on each other due to the kinematics or the geometry of the problem. In contrast, alpha, theta, and phi, these are all generalized coordinates because they don't have any dependence on any other coordinates, and they require no kinematic constraints to describe the motion of the system. Okay. So generally, when we're thinking about what generalized coordinates to use, if we're looking at rigid bodies, we generally want to look for motion of the center of the mass. For systems of particles, you can really just look for the motion of each individual particle, or perhaps apply like an Euler's law and look at the motion of the cluster as well. really this shows up in rigid bodies where you can use a lot of different coordinates to describe that motion. And you want to really stick to using center of mass coordinates and rotation about center of mass as well. That being said, sometimes you might have a rigid body that's pinned at a location, and then you'd want to describe the motion of that rigid body with respect to that pinned position, so an angle with respect to that pin joint. Okay, any questions on this? Okay. In that case, we're now going to talk about the principle of virtual work. This is a method that we're going to use in order to deal with forces, external forces or non-conservative forces specifically when we deal with the Lagrange equation. It's also a technique for deriving equilibrium points. And it's really just, in essence, a statement of static equilibrium. And it's what we would consider to be the first variational principle of mechanics. All right, so we're going to consider here a system of n particles in 3D space, each with coordinates xi, yi, and zi for I equals 1 up to n. We're going to define what we call virtual displacements, which are instantaneously infinitesimal changes in the displacement or position of each particle. And we're going to say that these are delta xi, delta yi, and delta zi. These virtual displacements have to be consistent with your kinematic constraints. So for this pendulum here, this system the virtual displacement can't send the pendulum further than the length of that string. Okay. Okay, so we're defining these virtual displacements. They have to be consistent with constraints, but otherwise they're completely arbitrary, hence why we're calling them virtual. So our coordinate here is x at t. We're going to say that our virtual displacement is delta x. For this pendulum, we would consider a delta theta as our virtual displacement. So we are simply thinking about a virtual displacement here and what is happening to the system when we have that displacement. It's not a real displacement, it's a virtual one. And we're assuming that this takes place instantaneously and that it simultaneously happens for all of the degrees of freedom at the same time. And they're independent of time as well. Okay, so this symbol delta here is what we're going to use to denote virtual. It is not a differential, but it does obey the rules of differential calculus. So it denotes virtual, but it's not actually infinitesimal. It's not like a dx or a dy. It's a delta x, delta y. But it still obeys rules of differential calculus. Okay, so the principle of virtual work states that if a dynamical system is in a state of static equilibrium, the virtual work performed by external forces and moments during a virtual displacement of the system is zero. And so that is, in a sense, a statement of static equilibrium, as you've seen before, but though now we're going to be using work to show that instead. We're going to consider our system of n particles, shown here. Each of them have their own position vector, Ri, their own mass, Mi, and then they have constraint forces acting on them, lowercase fi, and external forces, which is represented with a capital Fi. So given static equilibrium, we should know, or be able to show at least, that the sum of the forces, that is Fi, big Fi, plus little fi, this is equal to 0 and is true for all of the particles due to static equilibrium. So then we can write that the virtual work, we'll use delta W sub I. This must be equal to those forces, big F sub I plus little f sub I, dotted with our virtual displacement, delta Ri. And that must be equal to 0. We're going to go ahead and expand this dot product. And we will get that big Fi dotted with delta r I plus little fi dotted with delta r I. That must be equal to 0. We said previously that the virtual displacements are consistent with the kinematic constraints. And what that then tells us is that the second dot product here, this is actually going to just be 0 due to that. Then as a result, what we find here is that the summation from I equals 1 up to n of f sub I dot delta Ri, this is equal to 0. And this is the principle of virtual work. When we deal with the examples for the Lagrange equation, we'll see how this is actually applied and actually used, because that's where we're going to apply and use it, is in Lagrange equation. All right, any questions so far?
Why is little f dot r 0?
So it has to do with the alignment of constraint forces and how they act. So this is not something we're going to go too deep into, but effectively the constraint forces are in the same directions as these displacements, as these virtual displacements. Any other questions? Okay, in that case, we are going to continue on. Okay, so if the coordinates that we've chosen are linearly dependent, then we're going to need to introduce a coordinate transform to construct a set of linearly independent generalized coordinates. And we're going to call generalized coordinates these q1 up to qn. Now in this case, when the coordinates that you first start with are linearly dependent, that implies that there's an underlying constraint equation. And as a result, the number of generalized coordinates is going to be less than the number of coordinates that you selected when you started this. Okay, so in that case, we're going to write that our position vector, Ri, is now equal to Ri, which is a function of q1 up to q little n. And this is true for, in this case, it's so I equals 1 up to big N. And then we're now going to apply this virtual displacement to this coordinate system, and we're going to have to do a chain rule. We're going to get that the summation from I equals 1 up to big N of big Fi dotted with the quantity, the partial of Ri over partial Q1 times delta Q1 plus plus partial of Ri with respect to partial Qn times delta Qn, and all of that is then equal to 0. From the principle of virtual work, we then know that, we can then write that the summation from I equals 1 to big N of big F sub I dotted with the summation of, we're going to use K equals 1 to little n, a partial Ri over partial Qk. This must be equal to 0. We still need a delta Qk here. That's equal to 0. And then we're going to bring in the F dot inside. We're going to get summation from I equals 1 to big N of the summation from K equals 1. Oh, wait, actually, hold on. Let me start over. We're going to switch the order. We're going to have the summation from K equals 1 to N times the summation of I equals 1 to big N, and I'll give you a moment to rewrite that. And by the way, the lectures are being recorded, and I'm going to post them online, so you don't need to take pictures of everything. I'm not going to post the completed notes, but you'll get the recording from class that's shown on the screen right now. Okay. We have a parenthesis, and then we have big F I dotted with partial Ri, Ri over partial Qk. All of that times delta Qk is equal to 0. And from this, we can define what we call generalized forces. We're going to call everything inside this little brace, we're going to call that Q sub k. And Q sub k here is the generalized force in this case. So what we have done is we've taken the coordinate or the forces, external forces, as expressed in our chosen coordinate system, and we have transformed that into forces acting on our generalized coordinates. So you could start with a pendulum and using Cartesian coordinates and use your forces in that Cartesian coordinates and then define a transformation to take that from Cartesian into something like polar coordinates as well. So if you choose coordinates that are not generalized, you can transform them and find generalized forces. It's just generally better to start with generalized coordinates though, to be honest. Yeah, I think there's either an example problem posted on Canvas or I intend to post one. If there isn't one posted, let me know and I will figure that out. Are there any questions before we move on to Lagrange's equation? All right. Okay, so Lagrange's equation is an energy-based method for computing equations of motion, and it relies on generalized coordinates. This is why we started with generalized coordinates. We're going to consider kinetic energies and potential energies as function of our generalized coordinates. And we're going to say that the generalized coordinates are q, little q sub I, for I equals 1 to n, such that our kinetic energy, which we're going to use big T, is equal to T, function of q1 dot, up to q little n dot. And the potential energy, big V, is equal to big V, a function of q1 up to qn. We're going to then define a quantity that we call the Lagrangian, or big L, and this is just going to be equal to L will be equal to the kinetic energy T minus the potential energy V here. This is a quantity we call the Lagrangian, and it's the difference between the kinetic and the potential energy, whereas the total or the mechanical energy was the summation of these two. Okay, once we compute our Lagrangian, Lagrange's equation is then given as d over dt of partial L over partial q I dot minus partial L over partial qi, and this is then equal to our generalized forces q, big Q sub I. So in this equation, we are going to be taking derivatives of the Lagrangian, or big L, with respect to the generalized velocities and the generalized displacements. And we're going to ignore the fact that those two velocities and the displacements, we're going to ignore that they're related. We're going to treat them as being independent variables with no connection or relationship to each other, and we're going to take the derivatives of this Lagrangian with that in mind. And we're going to determine our generalized forces using the principle of virtual work. So that's where this comes into play. Okay, so we can just note here that from principle of virtual work, the virtual work done by non-conservative forces is equal to summation from I equals 1 to little n of big QI times delta little qi. Just a restatement of that. Okay, we're now going to go through just a general solution procedure, and then we're going to do some examples, which will be a mixture of me doing stuff and you guys doing stuff as well. Okay, so in a general solution procedure is we're going to define a coordinate system, we're going to determine position vectors, we're then going to determine velocity vectors. We don't need to find acceleration vectors here because we don't have a need for those. We're then going to compute the kinetic energy, the potential energy, and any virtual work done by non-conservative systems. For some systems, you can skip the kinematics. That's steps 1 through 3. For many systems, you just cannot. That's quite simply how it goes. In all of the examples we're going to go through, I'm going to go through all 6 of these steps just so that you have a complete solution, whether or not I needed to do that or not, or you need to do that. We're still going to go through everything. Before we start this example 4, are there any questions on what we're looking at? All right, let's take a 2-minute break, and then we will, let's say a 1.5 minute break, and then we'll start example 4. All right, let's come back together, and we're going to go through example 4 here. We're going to consider a pair of coupled oscillators that slide with friction along the ground. The coupling spring includes both a linear term, that has stiffness K2, and a nonlinear cubic term with a stiffness alpha, so that's alpha times the relative displacement cubed. And there's an external force acting on the second mass, and we've also included gravity here as well. So we're going to go, and we're asked to determine the equations of motion using Lagrange's equation. Okay, so I've gone ahead and redrawn the problem here. We're going to start by defining a coordinate system. In this case, we're just going to use a simple Cartesian coordinate system, your standard Cartesian at O. So we'll define a unit vector I in the horizontal direction, unit vector J in the vertical direction, and then we're going to have that that counterclockwise rotation is positive. We're then going to define position vectors. We're going to start by drawing a position vector to each mass from the origin. We'll have an R1 here, an R2. So R1 is the position vector for the first mass, R2 is the position vector for the second mass. We'll assume that x of t and y of t here are measured from the position of static equilibrium. And then in order to define these position vectors, we're going to need to add a few dimensions here. So we're going to say that this dimension right here, we'll say that's A, and then up to here, we'll say that is little b. So then our position vectors are R1 is equal to A plus x, and x is a function of t here in the I direction, plus 0j. R2 equals, in this case, b plus y in the I direction, plus 0j. We're going to go take time derivatives of these position vectors to compute the velocities. We're going to find that R1 dot is equal to x dot I, R2 dot is equal to y dot j. So this is a type of system where you can skip the kinematics because it's a rectilinear motion in a single direction. For the next example problem, it's one where you won't be able to skip kinematics. You'll need to understand that. Okay. From here, we're going to compute the kinetic and potential energies, and then we're going to look at the virtual work done by the non-conservative forces. So first off, what are the there's a question, yes?
Would that be y dot I for j?
Yeah, absolutely. Yeah, it should be y dot I because it's in the I direction. Absolutely. Yeah. Any other questions? Okay, what are the non-conservative forces acting on this system?
Friction.
So friction is one. On what body? So friction acting on both bodies. Yep. Are there any other non-conservative forces? Damper is another one. So both friction on both masses and the damper act to reduce the energy in the system. Is that all of the non-conservative forces? See a few nods. Say a thumbs up. Okay, if somebody doesn't answer me, I'm going to start assigning more homework. And I don't want to do that because I don't want to have to solve that. Yeah. Gravity? Gravity is a conservative force, but I appreciate you answering. So we have friction, the damper, and then those are absolutely non-conservative. We now know that gravity is conservative. What else is conservative in this system? What are the other conservative forces? The springs are conservative. Anything else? Say double thumbs up now. I see a hand.
Normal force?
Yeah, that is a good question. So the normal force will be a conservative force, but it actually is an internal force that we won't actually care about in all honesty, except for calculating friction. Outside of that, we wouldn't care about it. But yeah, it would be conservative in this case.
Do we have any assumptions going into this problem?
Did we have any assumptions? So we're assuming that there is only kinetic friction, so we're ignoring static friction. We're assuming that the x and y of t are measured from static equilibrium, so we don't need to worry about the unstretched lengths of the springs. And those are our major assumptions. Yeah. So F of t is the missing force. Now, is it conservative or non-conservative?
If you're doing work to the system with F of t, so it's like increasing the overall energy in the system, so
Which means that it is
non-conservative.
it's a non-conservative force. So this external force acts to inject energy into the system, or potentially suck energy out, depending on what it's doing. Nevertheless, it is preventing the energy from being constant, is therefore a non-conservative force. So our non-conservative forces, first we have friction, second we have the damper, and then third we'll just say F of t, the external force applied to this system. All right, we now need to compute the kinetic and potential energies, and then we'll deal with the non-conservative forces. So what I want you guys to do is work with your neighbors to compute the kinetic and the potential energies, and then as a class, we will do the non-conservative ones, and I'll show you how you do that with using the principle of virtual work. And it'll take about 5 minutes to do this, and I'll come walk around.
I think it's one half like oh, beta is just oh wait, that's gonna be virtual.
All right, let's come back together. Majority of you were able to get the kinetic energy. Kinetic energy, I'm just going to write KE here. Oops, not KE. Kinetic energy, big T, was equal to, in general, 1/2 M1 times the vector r dot 1 dotted with itself. That's the vector form of kinetic energy, plus 1/2 M2, R2 dotted with itself. And then this ends up being equal to 1/2 M1 x dot squared plus 1/2 M2 y dot squared. And so it's your standard kinetic energy for an oscillating mass. We're going to look now at the potential energy, or the PE in this case. For this system, that is going to be, big V is going to be equal to 1/2 K1 times x squared. So the deformation of this spring with K1, that is purely just x, meaning that for any value of x, the force produced by that spring is going to be K times x, and therefore the potential energy is 1/2 K1 x squared. The coupling spring, so this coupling, when I say coupling here, I just mean it's a spring that connects two things together. That's all that I mean by coupling. Same when I say coupling damper, it just means it connects the two things. We would call this spring the grounding spring, and then the one that connects the two masses the coupling spring. And that's simply because the spring on the left connects the first mass to ground. Okay. And if there was a damper there, I would say it's the grounding damper. So in this case, it's going to be 1/2 K2 times the quantity, it's going to be y minus x, and the whole quantity squared, because it's the relative displacement across the spring that determines the potential energy. And then for that nonlinear spring, we're going to have 1/4 times alpha, and it's going to be the relative displacement, but this time it will be relative displacement raised to the 4th power. Okay, we're now going to deal with the non-conservative forces. So we're just going to write out what they are. So first we had f of t. Second, we have the damper. The force given by this thing is c minus c times y dot minus x dot. That acts in the I direction. And then the third is friction. We got two friction forces. We'll just write them out together as a whole. We're going to have minus mu m1g times the signum function x dot minus mu m2g the signum of y, it's y dot, all of that acting in the I direction. Yeah.
Where'd you get the 1/4 from?
Yeah, so that has to do with the, so this force in the spring is x cubed, alpha times x cubed. And so when we integrate that to get the energy, we will end up with a 1/4 coming down. Yeah. Okay, so these are the forces as expressed in our coordinate system, or our chosen coordinates. If we were using a different set of generalized coordinates, we would then need to apply the transformation that we discussed earlier. In this case, because it's a rectilinear motion type problem, it will end up keeping the same forces that we see up here. And I believe in one of these examples, we won't deal with that transformation, but you'll see how the forces are different once you apply principle of virtual work. Okay, so from the principle of virtual work, we know that delta WNC is going to be equal to the summation of the non-conservative forces dotted delta Ri. In this case, delta R1 is equal to just a delta X in the I direction. Delta R2 is equal to delta Y in the J direction. So we're summing up all of the forces with that dot product, and we're going to write this out as delta WNC is equal to minus C x dot minus y dot times delta x minus mu m1 g times the signum x dot delta x minus C y dot minus x dot delta y minus mu m2g times the signum of y dot delta y plus FOT times delta y. We won't have a delta x times f of t because f of t only acts on the second mass. So we can then go and group like terms, and we'll find that delta WNC is equal to the quantity minus C times x dot minus y dot delta x minus mu m1g times the signum of x dot, and then all of that times delta x plus the quantity minus C times y dot minus x dot minus mu m2g times the signum of y dot plus f of t, and that's multiplied by delta y. Just going to move this down. Everything inside the first square bracket, that's our big Q1, so that's our generalized force Q1. Everything inside the second bracket, that's our big Q2. From here, we're going to compute the Lagrangian. We'll say L is equal to T minus V, which is equal to 1/2 M1 X dot squared plus 1/2 M2 Y dot squared minus 1/2 K1 X squared minus 1/2 K2 X minus Y quantity squared. Although I think earlier I wrote it as Y minus X, right? The order doesn't matter because of this squared, but I'm going to erase it and rewrite it just for consistency. So we got Y minus X here, and lastly minus 1/4 times alpha X cubed. So that is our Lagrangian. Oops, that's not right. That should be Y minus X to the 4th. Okay. Were there any questions on those non-conservative forces and the principal virtual work, or on the Lagrangian that we just computed?
When you dot the damping force with the with your fictive differentials, why does one of the damping forces flip sign and the other one stays the same?
Yeah, that's a great question. So I need to think about that. I know this is right, but I don't want to give you that it's right because I say it. So I want to give you an analytical reason. Let me deal with this outside of class. I'll analyze this and I'll come back and tell you on Wednesday. It has to do with what we can call reciprocity, but that's not that doesn't help you at all. So let me get back to you on that. Are there any other questions? Yeah.
So for the spring constant, like K or alpha, like depending on whether it's cubic or under the second degree, the 1 over something and the exponent is just plus one dimension.
Yeah.
Okay.
Yeah. So let's just do a little aside here. So if the force by some spring is equal to alpha times x to the n, where n is some integer, let's say. If n is not an integer, then it's a different discussion. Then the potential energy is going to be equal to alpha over n plus 1 times x to the n plus 1. That will be the potential energy of that spring. Yeah.
I'm not sure if I'm saying this right, but what is the sigma like that? I think it's the SGN.
Oh, did I not cover the signum in the previous lecture? A little bit? Okay. Give me a moment. We'll talk about that. All right, so the signum function, oops. Hold on, my pen is not working. Okay, if I can't get the pen to work, I'm going to just end up writing it on the board. Oops. All right, there we go. So the signum function of x is equivalent to the sine of x. So it's equal to 1 if x is greater than 0, 0 if x is equal to 0, or minus 1 if x is less than 0, such that the signum is always opposing motion. So this friction force is always going to oppose motion in general. Any other questions? Okay. Okay, we are going to continue and finish this example. I know it's a lot to absorb. We have a lot to cover in the class, but so we're going to progress and go ahead. We're going to apply Lagrange's equation. So that written out is going to be d over dt partial L over partial q1 dot, or I guess a qi, minus partial L over partial qi, and that's going to be equal to our generalized forces, qi, big qi. So this is going to be d over dt partial L over partial x dot minus partial L over partial x is equal to, we called it q1, so we'll just write that. And then the second one is going to be d over dt partial L over partial y dot minus partial L over partial x is equal to q2. And now we're going to go and compute each portion of each of these Lagrange equations. And we'll get as far as we can, and if we don't finish, we'll finish this on Wednesday. Is that a question?
Shouldn't that be a Y in the head?
It should be a y, yes. Yeah. Okay, so we're going to start off looking at the first equation for x. And the way I like to do this is I'm going to break it up into pieces, and I'm going to go step by step. So we're going to have d over dt partial L over partial x dot. It's going to be equal to d over dt times the quantity. So looking at our Lagrangian, we only have an x dot in the first term right here. There's no other x dot anywhere else. And we're going to ignore that this x is related to this x dot. We're going to ignore that and pretend that they're totally separate variables, meaning that we're only looking for terms that have an x dot in it. The only term that has that is here. We'll take a derivative of that. The 2 will come down, and we'll get m times x dot. I like to break this up and deal with each derivative separately. In this case, what's inside the parentheses is relatively simple, but you can end up with a lot of stuff inside there, and skipping ahead and doing derivatives in your head can lead to mistakes quite quickly. So now we're going to take the time derivative, and we'll get, oh, my pen is not working. We're going to get m1 x double dot. What is going on here? M1 I don't know what is going on with this pen. Connects. Okay, we get m1 x double dot. We'll then go and do the next part of the equation. X double dot. So the mass times the acceleration, m1. We'll then do partial L over partial x. This is going to be equal to, so we're going to look at every term that has an x in it. We've got a term here, we've got a term here, we got a term here. So all 3 of these terms, none of the kinetic energy terms have an x in it. So we're going to get here minus. All right. We're going to finish this next time. Just